Okay, so in this video, in this section, we're going to be finding limits, both graphically and numerically. Um, right, so in the last video, I think I mentioned the word limit probably just once, and I never really said what it is. And before we even talk about limits, I want to talk about something called Zeno's paradox. Zeno was a Greek philosopher, and Zeno was interested in motion, right? Things that move, right? How things move at all. In particular, if we start at a point, let's say we have an object at point A, and we throw it, right? And it ends at point B over here, right? Okay. So, we talked about measuring the distance and how long it took and finding the velocity and so forth. But here, let's just talk about the distance that it travels, right? The distance from point A to point B. And we can assume, let's just say it's, I don't know, 100 feet. So that's how far this, let's say we throw a rock, right? We throw a rock, it lands 100 feet away. Okay. So no problem, right? I mean, we do that all day. We throw things move, right? Things are constantly in motion. Doesn't seem to be an issue. Except Zeno had the following idea. So in order to get from point A to point B, right, it has to get halfway there. Right? It has to get to this point, say 50 feet, right? You can't go 100 feet without first going 50 feet. Right? That's reasonable, right? So yeah, halfway there, right around here, it traveled about 50 feet. But to get to this point, to get to 50 feet, you have to get halfway there, 25 feet, right? Because you can't get to 50 feet without first going to 25 feet. Okay, just keep going, right? That means it has to get halfway there too. It has to get to 12.5 feet. And then it has to get halfway to that point, and then halfway to that point. And you can see that there's always going to be another halfway point. Now, this might get very close here. Let's blow this up a little bit. Right? Let's say that this whole thing here is just here, right? So this is 0. And let's say this is, I don't know, half a foot. Right? So right around here, it's just 1/2 of a foot, right? Right, so this keeps going all the way to 100 feet eventually. Well, to get from 0 feet to 1/2 of a foot, guess what? You have to go halfway in between. So you have to get to 1/4 of a foot. And then to get from 0 to 1/4, you have to go halfway there. You have to get to 1/8 of a foot. And then 1/16 of a foot. That's a 1. And then 1/32, and so on, right? The point is you can always divide these further and further into halves. So in order to go anywhere, you're going to have to divide this infinitely many times. So it's going to take forever, right? Because infinity just basically means forever, right? It'll take you forever to go anywhere. In other words, motion is impossible. We can't go anywhere. Because in order to go from any point to any point A to any point B, well, you have to get halfway there first. And then to get to that point, you got to get halfway there, and then get halfway there, and then get halfway there. And of course, at some point, you're just going to keep going, and you can't get anywhere. Because it's going to take infinitely long just to go that tiny distance, right? So Zeno claimed that you can't go anywhere. Motion is impossible. That we should be living in a completely static universe, right? Everybody should be standing completely still, no motion whatsoever. Of course, that's that's a paradox, right? Because we're moving all the time. I'm moving my pen, right? I'm moving my mouth. I'm just moving. So motion is obviously not impossible. Of course, it's possible. Right, the world is constantly in motion. Okay, so obviously this little argument here is absurd, right? We have to be able to move. So I'm not going to be able to resolve this paradox. Of course, you might try to, find the hole here. What's going wrong? What's wrong with this argument? The argument is that you have to divide this up into infinitely many intervals, and infinitely many means that each one will take forever. But of course, if you're talking about time, it's not going to take you that long to go this tiny distance, as it would to go, say, from 50 feet to 100 feet. Right? That would take longer. So essentially, Zeno was thinking that because you're adding up infinitely many numbers, that it would essentially add up to infinity. Right? But that's not what happens. Right? We're adding up all these numbers here, and it's true, there are infinitely many of them, but because they're getting smaller and smaller, it turns out that you can add up an infinite number of numbers and still get a finite number. In this case, you just get 100 feet. Right? Yeah, so that may not seem, well, you may not buy that argument, but because it's one that, we have to talk about things that are called infinite series. And we're not going to do that. That's going to be the next semester. Right, so that's Calc series. I can't spell series here. Series. That's going to be Calc 2. Okay, so in Calc 2, you'll go through this adding up all these numbers, right? You'll add up 1 plus a half plus a quarter plus 1/8 and so on. In fact, some of you probably have done this before. Some of you know that the answer is 2. But, So, again, you're adding up an infinite, right? I'm not writing all the numbers here. There's infinitely many numbers that I'm not writing. But because those numbers get smaller and smaller, they add up to a nice number, in this case 2. And in this case, we add up all these numbers, you get 100 feet, right? So 50 plus 25 plus 12.5 and so on will add up to 100. Right? Okay, so that's Zeno's paradox. What does this have to do with limits? So now we can talk about what a limit is. Limit is basically just getting smaller and smaller or closer and closer to something, right? So we want to get closer and closer and closer, right? You can get as close as you want, but without getting there, right? I mean, you might get there, but limits only care about the closer and closer and closer aspect of it. Okay? So let me sort of reverse the argument here. Like, let's just go from 0 to 1. Okay, so here's 0. We want to end up at 1. Okay, so in order to go from 0 to 1, we have to get halfway there. Right? So we have to get halfway there. We get to 1/2. Right? So now we know we can go from 0 to 1/2. Right? Right? Motion is obviously entirely possible. Happens all the time. Right? But to go from 0 to 1, you got to get halfway first. Right? Now, to go from 1/2 to 1, well, you got to get halfway there as well. So that's 3/4. Right, so now we're 3/4 of the way there. Then we have to keep going, right? What's halfway to 1? It's going to be 7/8, right? And then again halfway will be 15/16. And then right in there, halfway there is going to be 31/32, right? Maybe make that a little bit bigger. 31/32. And we can keep going, right? Halfway there, we're going to get to 63 over 64 and so on. So these numbers, 63 over 64, is not 1. It's a little bit less than 1. But you can see this is close to 1. Right? It's not that far off. Right? Of course, you can get even closer. Right? If you want to get closer, it's going to be very hard to see here, but you can get to 127 over 128. And that's still less than 1, but it's even closer to 1, right, than the 63 over 64. Right? And if you want to get even closer, you can go 255 over 256, and so on. Now, I'm using these numbers because I'm dividing them in halves, but we don't have to divide by half, right? We can just go from 0 to 0.9, and then we can go to 0.99, and we can go to 0.999, and then 0.9999, and these are also getting close to 1. In fact, this is much closer than this number, right? Because the difference between these two numbers here is very tiny. It's 1/10,000th, I think, right? 0.0001. Right? Yeah, when you add these, you get 1, right? So the idea here is we're picking numbers that are closer and closer and closer to 1, but are not equal to 1, right? If you reach 1, if you reach this number here, you've gone too far, right? This is too far. So we don't want to get there. We just want to get as close as we want. Okay, so that's the idea, right? So yeah, I mean, look, in some cases, sure, you just go this tiny bit more and you get to 1. But the limit doesn't care what happens at 1. It only cares what happens when you get close to 1. Okay, so with that, let's do an example. And this is one that's going to be similar to one that's in your book, but not quite. Okay, so we're given a function. And again, if you're a little fuzzy on functions and you're not quite sure what a function is and all that, well, you can go back to the review chapter, but I'm not going to review it because that's something you should know from your algebra days. If you've never seen this before, this f of x, and I will tell you one thing about this, this is not f times x, right? Don't make that mistake. Typically when you write parentheses, right, you mean multiply. This means 3 times 5, which is 15. But this is not f times x, right? So f is just the name of the function, right? F is just the label for our particular function. Okay, so I'm going to erase all this because you should know this, that this is not f times x. Right. But again, if you haven't seen this before, this notation, you might be in the wrong class. You might need to take pre-calculus or even college algebra or something, because this is something you should have seen, I would say, hundreds of times by now, right? Okay, right, and so this is the function f of x equals x squared plus 4x minus 5 divided by x squared minus 1. So specifically, this is called a rational function. Rational meaning fractional. Numerator and denominator. And before we're going to talk about limits here, one thing you should talk about, anytime you see a function, you should ask yourself, what's its domain? Right? What do I mean by domain? I mean the set of all numbers x, right? The set of all x, the collection of all numbers x that are allowed into this function. In other words, the set of all x such that when I plug in x, f of x, I just get a number. In fact, it has to be a real number as opposed to, say, an imaginary number. Right? We're not going to talk about imaginary numbers that much in this class, but it may come up. occasionally, but we tend to ignore imaginary numbers here. Imaginary numbers are important in different contexts, but not in calculus, at least not what we're concerned with here. Okay, so what do we have to worry about, right? Well, because we have a fraction, and if you remember earlier, we said 0 divided by 0, right, is undefined or indeterminate. In fact, anything divided by 0, right? 8 divided by 0 is just not even a number. It's meaningless. It's not indefinite, it's undefined. It's undefined. We don't define it because it's not a number. Okay, so the point is you can't divide by 0. So in order for this function to make sense, this denominator better not be equal to 0. So when does it equal 0? Well, you just solve that quadratic equation. I'll give you 10 seconds to do that because it should be easy by now. Yeah, you just add the 1 to both sides, take the square root. Don't forget the plus or minus, right? And the square root of 1 is just 1. So we get x equals positive 1 or negative 1, right? And so that's where this would be 0. But remember, we do not want the denominator to be 0, right? So when is x squared minus 1 not equal to 0? When x is not plus or minus 1. You can think of the plus or minus 1 as the bad numbers, what we call restricted values. Right? They're not allowed. Restricted values of x, right? So to answer our original question, what is the domain of this function? Well, it's the collection of all numbers x such that x does not equal negative 1 or positive 1. But all the other numbers are allowed, right? In other words, if you draw a number line, you just have to skip over negative 1 and positive 1. But all these other numbers are fine here. So all of these numbers here, all of these numbers here in between, and all of these numbers here. In other words, in interval notation, you're going from negative infinity to negative 1, right? And then union from negative 1 to positive 1, and then union from 1 to infinity. So hopefully you remember interval notation because we're going to be using this quite often in this course to talk about sets of numbers, intervals of numbers, right? Okay, so either way, you can represent the domain this way, or in some cases it'll be more convenient to write it this way in interval notation. Okay, so in other words, right, you're not allowed to plug in 1 or negative 1. And what I mean by that is if we try to plug in negative 1, you'll see we don't get anything. And if we try to plug in positive 1, same thing, it's undefined. You don't get a number. So the positive 1 and negative 1 here are restricted values. They're not allowed into the function. They're not part of the domain. Okay. Okay, so again, this is just a review, but now we want to talk about, again, this function. I'll copy it down here because we need to refer to it. So f of x was x squared plus 4x minus 5 all over x squared minus 1. Okay, so here's my question. What happens to f of x, right? In other words, these are the y values. What happens to the y values when x approaches 1, right? The word approaches, right? Gets close to, right? So what happens when x gets close to 1? Right? We don't care what happens when x equals 1. In fact, we already know the answer to that. When x equals 1, there is no y value. It's undefined. But maybe something happens when x gets close to 1. So let's see, right? So there's a couple ways of doing this. One is to draw the graph, but I'm going to do that later. Instead, I'm going to make a table. Right? It's a table of numbers. Now the book likes to do this horizontally. I prefer to make a vertical table here. Okay. So this is my x column, and then this is my y column, y just being f of x. Okay. So what numbers are we going to plug in for x? Well, we tried plugging in 1, and we saw that that did not work. Right. We tried that up here. It's not in the domain. Trust me, it won't work. What you'll get is 0 divided by 0. But remember, 0 divided by 0 is meaningless. It's not an answer. Right? So when x is 1, y is, well, nothing. It's undefined. Okay? But we can plug in numbers that are close to 1. So what's close to 1? How about 0.9, right? As a fraction, that's 9 over 10. That's pretty close to 1. Okay? And so what happens when you plug in 0.9? Well, you get a number. You get 3.666666, and so on. Right? So it's roughly 3.6667 or so. Okay, so that might not tell us much, right? But it is a number, right? It's a perfectly good number for the y values. Can we get even closer? Sure, we can plug in 0.99. And if we plug in 0.99 into the same function, oh, hang on, I plugged in the wrong number here. It's not 3.6666. Oh, shoot. Yeah, I'm glad I caught myself here. Again, look, if you see me making a mistake anywhere, please send me an email and point it out, and I will correct it, probably in the description. Okay, so when you plug in 0.99, maybe we should do that. Let's just plug in 0.9, right? So here's the function, right? So everywhere I see an x, just change that to 0.9. So we have 0.9 squared plus 4 times 0.9 minus 5. Sorry, it should be a 5. And then divided by 0.9 squared minus 1. Again, don't try to work that out by hand. You can. It might take you a while. This is why we have calculators. So just plug it in your calculator. And I'm getting something like 3.1053. Okay, so yeah, it wasn't 3.6, it's 3.1053. I'm rounding to 4 decimal places. If you want to round to further decimal places, that's fine. Usually 4 is enough, but in some cases you might have to keep going. Okay, all right. So now do the same thing with 0.99. And instead of writing this out, I'll save you the trouble. Just plug the same numbers in your calculator, but use 0.99 instead of 0.9. And now you should get something like 3.01005. Okay. And can we get even closer to 1? Sure, just add another 9. Right? Make it 0.999. All right, 3 nines. And when you plug that in, you get 3.001 something. But I think we see a little bit of a pattern here, right? As these numbers get close to 1, these numbers seem to get close to 3, right? I mean, 3.001 is close to 3. And if you got even closer, and I'm going to run out of space here, but if you added another 9, you're going to get 3.0001. So you're just adding more zeros, right? So it looks like y is getting close to 3, right? Y gets close to the number 3. So sloppy 3, but there, all right, so there's the 3. But notice that I'm only plugging in numbers here that are slightly less than 1. There's no reason why we can't plug in numbers that are bigger than 1. So what's bigger than 1? Well, 2 is bigger than 1, but it's not very close to 1. Well, okay, it's the closest integer, but the whole point of real numbers, right, is that we can use decimals. So why don't we start with 1.1? If we plug in 1.1 into the same function up here, right, same function, same x for 1.1, let's see, you're going to get 2.905, approximately. But I can get closer. I can plug in 1.01. That's even closer to 1. And then the y value will be 2.995 something? 2.99 something, right? And if you add another 0, 1.001, that's much closer to 1. And then you just get 2.9995, I think, or 05. It doesn't matter. 2.999 is also very close to 3. So from both sides, right, this is from the right side of 1. Remember, if this is 1, right, when x is bigger than 1, you're to the right. And when x is less than 1, you're to the left, right? So, right? So from the left side, when you're less than 1, y is bigger than 3, slightly bigger than 3. And from the right side, when y is slightly bigger than 1, when x is slightly bigger than 1, y is slightly less than 3. Okay? So, in short, y just gets close to 3. Right. So the question is, why then, if this is the original function, I'm going to copy it down one more time. This one, right? When you plug in 3, you get nonsense. You get 0 divided by 0, which is not a number. Right? But when you plug in numbers that are close to 3, I'm sorry. We're not plugging in 3, right? We're plugging in 1. We're plugging in 1. X equals 1. That's undefined. Phew. Sorry, I'm getting a little sloppy here. Right? So, yeah, when x is 1, here we go. Y is undefined. We don't get a number here, right? We get nonsense. Oh, and I'm running out of space. Okay. Right. But when we plugged in a number like 0.9999, we got something close to 3, right? Maybe 3.0001, which is about 3. Not exactly 3, but pretty close to 3, right? And likewise, we plugged in a number slightly bigger than 1, 1.00001, and you probably get something like, nope, not 3, 2.9999005 something, but that's also very close to 3. It's approximately 3. And yet, when you plug in 1 by itself, you don't get 3. Right? You don't get 3. You get nothing. You get not 0. You get undefined. It's not a number. Okay? So this is the whole idea of a limit, right? Remember we talked about limits? A limit, right? We want to get closer and closer and closer to x equals 1. I should say x equals 1. Without actually getting there. So what happens when x gets close to 1? Y will get close to 3. Okay? So since I'm completely out of space, I'm just going to write down the summary of what we've done here. But make sure you understand how we got this 3 here. We got it by using this table here. By plugging in numbers closer and closer to 1, both went right to the left of 1 and to the right of 1, less than 1 and bigger than 1, but very close to 1. Okay, so to summarize, as x approaches 1, the function f of x, that is the y values, approach 3. Right? So f of x approaches 3, right? And we can also say this by saying that the limit, right, the limit of the function, the same function here, as x approaches 1, is equal to the number 3. Okay, so this is what we mean by a limit. All right. Right. So how did we calculate this limit? We used the table. Right? We did not plug in 1. Right? F of 1 is not equal to 3. In fact, f of 1 is not equal to anything. It's not a number. Right? So we calculated this 3 not by plugging in 1, but by plugging in numbers close to 1, numbers that approach 1, like 0.9, 0.99, 0.999, right? Or if you're bigger than 1, 1.1, 1.01, 1.001, right? So yeah, if you look a little bit back, you'll see that those are the numbers I plugged in for x, right? And they were close to 1, but not exactly 1. And so f of x seems to be getting close to 3. Again, not exactly 3, but 2.999 is awfully close to 3. Right? And 3.00001 is a number that's very close to 3. So they're getting closer and closer to 3. The closer x gets to 1, and maybe let's write this down because this is important. Right? The closer that x gets to 1, right, then the closer f of x gets close to 3. So that's the idea of a limit, right? Now, writing this any one of these ways just gets to be very tedious. So as mathematicians go, we like to abbreviate, and so here's how we're going to do it. We don't even write the whole word limit, right? It's only 5 letters, but we bring it down to 3 letters. LIM is the abbreviation for limit. And x approaches 1, we write x with a little arrow and then the 1. So this reads the limit as x approaches 1. I want to write all that. Yeah, x approaching 1. Of the function, in fact, we can write f of x, but I'll write the actual specific function here, x squared plus 4x minus 5 divided by x squared minus 1. Right, that limit is just equal to 3. And we got that by using the table. Okay. Right, so that's one way to calculate limits. Use a table. In fact, here we go again. Right, you can't plug in 1 by itself, it's undefined, but you can plug in 1.1, 1.01, 1.001, and so on. And, that's when x is bigger than 1. When x is less than 1, you can plug in 0.9, 0.99, and you can even get closer, 0.9999. And if that's not close enough, just add more 9s. You can add as many 9s as you want. Right? But you can't get to 1, though. Once you get to 1, remember, you don't get anything. It's undefined there. But these numbers, the y values here, get closer to 3. And these y values also got close to 3, so in the limit gets to be 3. Okay, makes sense, I hope. Again, maybe it doesn't make sense yet, but as we do more examples, I think you'll see the idea here. All right. So, yeah, let's do another one. Right, so I'm going to use the same function here. So let's go down here and just use the same function, f of x, what was it, x squared plus 4x minus 5, all over x squared minus 1. Right, and remember what the domain was. Right, the domain was all x not equal to 1 or negative 1. So again, that's part of the reason why I picked x equals 1. right? Why are we approaching 1 here? Well, no reason, right? We could approach 2. We could approach, 50. We could approach 36. We could approach pi, right? I just picked 1 because it works out nice for this function here. So we can also approach another number. How about -1? Right? So in this example, we want to calculate the limit as x approaches not 1, but -1 of the same function, f of x. Okay? So what is that limit? Right, so right now, the only way we know how to do this is to make a table. So I'm going to draw a similar table here. Right? But now, the center will be -1. We want to plug in -1. Well, if we plug in -1, we know what happens, right? It's undefined. But that's not how to calculate the limit, right? The limit is not what happens when x equals -1. It's when x is close to -1. Right? So what's close to -1? Well, now if you're bigger than -1, say -0.9, or -0.99, -0.999, and so on, right? Or if you're less than -1, -1.1, -1.01, -1.001, and if you want to get even closer, just keep adding more zeros. Or from the other direction, just keep adding more 9s. And you'll see that this generally will be close enough. You'll see a pattern here, right? You'll see something going on. But if you don't see a pattern, then by all means, just keep adding 9s or keep adding zeros, right? Okay. So, again, I'm not going to show you how to plug these in here. You're just plugging in these numbers into this function. Oops, yeah. So mostly you're just using your calculators here, right? So long story short, I'm going to plug these numbers into my calculator. In fact, I already did that, so I'm just going to write out the table here. So for -0.9, y is going to be, I think, 41. And then for -0.99, we get 401. For when x is -0.999, y is going to be 4,001, right? And for this number, -0.99999, I think we get 40,001. Okay. What happens from the other direction? For -1.1, we're going to get -39. And then when x is -1.01, you plug that in, you get -399. And then for -1.001, y is going to be -3,999. And for this number, y is going to be -399,999. Right. So what's happening here? What's going on with these numbers? Well, right, when x is getting close to -1 from the left side, right? In other words, oh no, I'm sorry, from the right side, when x is bigger than -1, these numbers here, what are they getting close to? They're not getting close to 40,000, right? Or actually, I think I'm missing a zero here. This should have been 400,001. I forgot there's an extra 9 here, right? So, yep, and they're not getting close to 400,000 or 4 million or 4 billion or 4 trillion. Right? These numbers are just getting bigger. These just get bigger and bigger and bigger. Right? They get huge. They blow up. Right? So we have a symbol for that, right? When something gets bigger and bigger and bigger, we usually refer to that as infinity. Right? Infinity is just the idea of what happens when you get bigger and bigger, right? It's right. It's just the it's just getting larger and larger, right? So what happens from the other side, right? When x is less than -1, these values are also getting bigger, except they're getting more negative, right? So on the number line, right, when you're going to the right, that's the positive direction. When you're going to the left, that's the negative direction, right? So here, these numbers seem to be getting closer to negative infinity instead of positive infinity. And they're two different infinities, right? Positive infinity means you're going to the right forever. Negative infinity means you're going to the left forever. And they're not the same thing. Okay? So what's the answer to the question here? What is the limit as x gets close to negative 1? What are the y values getting close to? Well, they're not getting close to any particular number. Remember, these are not numbers. Infinity is not a number. It's an idea. It's a concept. It's the notion that there is no biggest number, right? Right? And don't say, well, infinity is the biggest number, because it's not. It's not a number, right? It's the old joke of saying just take infinity plus 1. Well, that's bigger than infinity, right? No, it's not. It's the same infinity, right? Infinity times infinity is still infinity, right? It's all just infinity, right? There are, of course, different types of infinity, but we're not going to worry about that, right? For our purposes, infinity is infinity. It's just the idea that there is no biggest number. Any number that you can think of, right, has a bigger number. Right? So infinity is not one of those. It's not a number. Okay. So back to the question then, what is the limit? Well, there isn't any. There is no limit here. Right? It's not infinity. It's not negative infinity. We give up and just say there is no limit. Or specifically, we can say that this limit fails to exist. This limit does not exist. Okay. So that's the answer. It might be unsatisfying, but we drew the table here and we see that these numbers don't get close to any one particular number. In fact, they just get bigger and bigger, either positively or negatively. Right? So they don't get close to any one particular number. So the limit does not exist. And if you like to abbreviate DNE for does not exist, I'm okay with that. I'll probably do the same thing in some cases. So that's the idea, right? So just because you have a function and x is approaching a particular number, in this case, x is approaching negative 1, that doesn't mean that there's going to be a limit. Like there was in this example where the limit was 3, up here on the right, right? Here, there is no limit. It just depends on what x is approaching. Okay? And maybe we'll do one more just to make this clear here. Okay, so same function, one more time. Well, okay, I'm going to use this function a lot in this video. It's a good example. It's a good example. And now we want to find the limit as x approaches 2. Okay, well, again, we're going to do this numerically the way we've been doing it. Numerically just means draw a table. Right? Here's your x's and your y's. Now we want x to get close to 2. Or you know what? I changed my mind. Let's make it 2.5. Right? So x is getting close to 2.5. 2.5, right? So what's close to 2.5? Well, 2.4, right? Or even closer, 2.49. And that's already pretty close. How about 2.499? And that's probably close enough. If you want to get even closer, I'm going to squeeze one in here, 2.4999, right? And these are numbers less than 2.5. Bigger than 2.5, we have 2.6, right? 2.51, 2.501, and 2.5001. These are very close to 2.5, right? Okay, so now we just fill in the table, and again, that's tedious because you got to calculate each of these. So I'm going to fill this in very quickly here, but I'm going to use my calculator, and so this is going to seem magical that I'm going to fill all this in at once, but I'm going to pause for a minute, and I invite you to do this too. Actually, you should plug in these numbers and see what you get. So take a moment, plug in these numbers into this function up here, and see what you get. Okay, so yep, here it is. So this limit apparently is this weird decimal here. So it seems to be about 2.142857143. ... right? And again, that's very unclear from the table here. So if you're asking where did I get that number, well, I cheated. I actually plugged in 2.5 itself, right? Which, remember, you're not supposed to do that. You're not supposed to do that here. So let's plug in 2.5 and see what happens. So it turns out you get this number, 2.142875, which happens to be exactly 15 over 7. Okay. So really, yeah, instead of this is the approximate answer here. Trying to erase this here. There we go. Yep. The answer in this case turns out to be exactly 15 over 7. And as you can see, that's very difficult to get that from these numbers here. Right? You have to get even closer. And as I said, this is approximately 2.14285714285714285714. So you see a pattern here, right? And because there's that pattern, it's a repeating decimal. That's why it turns out to be a rational number, a fraction, 15 over 7. Okay. So like I say, this process is not always that easy to figure out the exact value. And this is one case where you really have to get very close. So if this is not enough information, you might have to plug in 2.5000000001, or maybe 2.4999999999, right? And if you plug those in numbers, these numbers in, you will get closer and closer to this number here. And again, it still may not be obvious that that's equal to the 15 over 7, but you should know how to convert a decimal to a fraction. Or at the least, make sure you know how you can use your calculator to convert a decimal to a fraction. Right? And it doesn't always work on your calculator, but it should work here. If you do this correctly, it should spit out 15 over 7, I think. Okay. Right. So remember I said I cheated here. I plugged in the 2.5, right? This is not how to find a limit. Right? Remember, the limit, we don't care what happens when x equals 2.5. All we care about is what happens when x is close to 2.5. What happens at 2.5 is irrelevant. Right? In terms of the limit. Right? Remember, we're looking for a limit here. Okay? Yeah. But it happens to give you the correct answer in this case. Right? If you looked at the previous two examples, right? Remember where we were calculating the limit as x approaches 1, and then the limit as x approaches -1. We tried plugging in 1 and -1, and we did not get the correct answer. When you plug in 1, it's undefined. But the limit is a perfectly good number, 3. Now when you plug in -1, it's also undefined. And it just so happens that the limit we don't say is undefined, we say it does not exist. So I know we're being a little bit pedantic here, right? Does not exist is not the same as undefined. Right? Undefined is what happens when you try plugging in a number into a function and you don't get a number. Right? We only talk about limits either exist or do not exist. Right? Here the limit exists. Right? Here the limit exists as well. But when x is approaching -1, the limit fails to exist or does not exist. Okay, so yeah, 3 good examples. Approaching 3 different numbers, right? 1, -1, and then 2.5. Okay, so we're not done with this example yet, right? Up until now, the way we've been calculating limits is this way, numerically. In other words, we made a table here, right? A table of values, a whole bunch of values, and you could use as many values as you want. Typically, I would do, 6 or 8, essentially 4 on each side, 3 or 4 on each side, right? And by each side, I mean, left and right, right? So here's use a different color here. Let's go back to yellow. So here's the number line, right? And right in the middle here is 2.5, right? So you want to plug in, say, 3 numbers or 4 numbers to the right of 5, right? So like 2.6, right? Or 2.501. And then, right, 3 or 4 numbers to the left, right? So 2.4, 2.49, 2.4999. And again, the book actually does this horizontally, which probably makes more sense. But I would run out of space doing this horizontally. There's just, the numbers are too many digits here, right? But that's the idea. You want to go, right, from the left and also from the right. So just keep in mind that, right, you're approaching 2.5. It looks like you're going to the left, but it's from the right side of 2.5. In other words, x is bigger than 2.5. And this is from the left side of 2.5. So x is less than 2.5. Right? And then 2.5 is right here in the middle. Okay, so I hope that helps. Okay, so remember, originally in the title of this section was finding limits numerically and graphically. So we did the numerical part. Now we want to do the graph part, right? So what I graphed here, or rather what I had a little piece of software that I have graph, is the function, right? F of x, right? It's the same function we've been dealing with here, right? And so, yeah, when you could just do this on your calculator. Your graphing calculator will give you similar picture here. So what do we notice about this picture here? So notice that as x is approaching 1 from both sides, y is approaching, well, this number here. I know this is hard to see here, but this is a 3. Right? So, yeah, 1, 2, 3, 4, 5, and so on. Okay. So notice what happens here. When you plug in 1, there is no y value here. There's no point here. This is a missing point. Mathematically, a missing point we refer to as a hole in the graph. Right? So there's a hole in the graph at x equals 1. Right? And that's exactly why when you try plugging in 1, we got, well, nonsense. We got 0 over 0, right? It's undefined. There is no y value here, right? And I know it's very hard to see, but there is a little hole in the graph there. Okay? So, yeah, the limit doesn't care what happens at the hole. It only cares what happens as x gets close to 1. In other words, the y values are getting closer and closer to 3. Right? That's where the hole is. Right? So we can say there's a hole right, at the point 1, 3, but 1, 3 is not part of the graph. Right? It's a missing point. It's a hole in the graph. Okay? So instead, the limit as x gets close to 1 of this function, that limit is 3. So effectively, when you're finding the limit, you're finding where the hole is, right? You're finding where, at least if the function is undefined there, then you're trying to find where the hole in the graph is, right? Because the y values here are getting closer and closer to 3 on both sides, left and right, top and bottom. Right? Yeah. Yep. Okay, so now we can see this, just looking at the graph, we can see that this limit had to be 3, because that's where the hole is located. Now, let's go on to this. The second question we asked was, what's the limit as x approaches -1? Well, let's see. So now, here, okay, so this is hard to see, right? Let me do a darker color here. Do a red. So over here is -2, right? Here's 0, that's the y-axis. So what happens when you're getting closer and closer to -1? Well, on the right side, this just goes up, right? Gets bigger and bigger. Remember, we were getting, 40,000 and 400,000. But when x is less than -1, right? So -1.1, -1.01, we were getting -39,000 something, right? These are getting smaller and smaller. And yeah, I cut off the graph here, but of course it keeps going. Right? So yeah, you've seen this before, right? Where you have effectively a graph that gets closer and closer and closer to a line. Right? That vertical line then is called an asymptote. So this is an example of a vertical asymptote. And so when you have that, again, the y values just blow up. They get bigger in the positive direction or bigger in the negative direction. And so we just say the limit fails to exist. The limit does not exist. Okay, there is no limit at -1. Or as x approaches -1, I should say. Okay. Right, and then the last example we had was what's the limit as x approaches 2.5 of the same function. Okay, so again, it's hard to see, but 2.5 is, well, here's 2, and here's x equals 3, so 2.5 should be exactly halfway between. So what do? You go up to the graph, and you say, well, as x is getting closer and closer to 2.5, what are the y values getting closer to? So the y values are getting closer to, it's going to be really hard to see here, but I'm going to try. Looks like just a hair under 2. Not exactly 2, but a little bit underneath 2. And if you remember, yeah, this was, oh no, you know what? I think I went the wrong way. I think it's a little bit bigger than 2. Yes, it is. It is actually bigger than 2. All right, let me try that again, right? So here's 2.5. If we go straight up, we get to this point here. We go straight across. Yep, it's a little bit above 2. I know you have to zoom in a little bit to see that, but it's a little bit bigger than 2. And it turned out to be exactly 15/7, right? Which is 2 and 1/7. Right. So yeah. Right. Now here there's no hole, of course. Yeah, so here there's no hole in the graph. So in this case, you can find the limit just by plugging in 2.5. Right. So this happens to equal the same thing that you get when you plug in 2.5 into the original function up here. But you don't want to think of it that way, right? Think of that as just a coincidence. It didn't have to be that way. In fact, remember, in the first problem, this was not f of 1. You cannot find the limit just by plugging in 1, because we got nonsense, we got undefined. And the same is actually true here, right? This does not exist is not the same thing as f of negative 1. F of negative 1 is undefined, which is not, it's a similar concept, but it's not the same thing as does not exist. So just because it's undefined, you cannot say it does not exist. Right? F of 1 was undefined, but the limit as x approaches 1 does not exist. The answer is 3. 3 exists. 3 is a perfectly good number. Okay, so yes, so undefined does not exist. In fact, it might not be, right? Here, undefined actually gave us, in the limit, we got 3. Here, undefined did not have a limit, but again, coincidence, right? So yes, so the way you calculate a limit is either by using a table or a graph. Right? There are other ways of calculating limits, which we'll do in the next video. Kind of a slick way, just using some algebra. But in this section, we just want to do it either by looking at a graph, and I know I messed up the graph a lot here, but I was trying to make a point, or using a table. In other words, plug in numbers that are close to this number here. Right? So I hope this is good. I think I'll do one more example, and then we'll move on. To, again, we're still going to be finding limits, but we're just going to be doing it in different ways. So I'm going to scroll down and just do one more example. Okay, so we want to find the limit as x approaches 0, in this case. And the function we're going to deal with, right, so we can give it a name. We can call it f of x again. The function is just the sine of x over x. You remember what the sine is, I hope, right? So how can we calculate this limit? Well, we have two options now, right? We can do it numerically using a table, or we can do it graphically by looking at the graph. And I'll do it both ways, right? There is a third way, but it uses a rather complicated technique, which we'll get to in the next section, I think. Yep. But let's just do it numerically, right? So, yep, so we'll make a table. Here's x, and here's y. Again, y in this case is just the sine of x over x. And we want to get close to 0. So what numbers are close to 0? Well, we have 0.1, 0.01, 0.001. Maybe I'll do another 0. And then, so that's bigger than 0. What about less than 0? Then you have the negative numbers, negative 0.1, negative 0.01, negative 0.001, and negative 0.0001. Okay. So again, you just use your calculator and plug all these in. So let me do that. Okay. So I got these numbers here. Right? For x is 0.1, y is 0.998334. And when x is 0.01, I got 0.99998333. If you're not getting these numbers on your calculator, it's possible that you're doing something wrong. Check your mode. When you look under mode, I think 3 rows down, it should say RAD and DEG, right? So one stands for radians, one stands for degrees. If you're not getting these numbers, your degrees are highlighted. What you want is to switch to radians. So highlight radians, hit enter, and then exit the mode, and then do this again. So, right? So the reason we want to do that, we want these numbers to be in radians, not degrees. Okay. If you remember from pre-calc, your trigonometry days, we talked about degrees a little bit, but generally speaking, mathematically, we much prefer to use radians than degrees. You know, in your science courses, your engineering courses, of course, you're going to use degrees probably more often, but you should know how to go from one to the other. And I'm not going to review that now, but it's look in your pre-calc book, and there should be a section on angles and how to convert from radians to degrees or vice versa. Okay. In any case, looking at the table here, I don't know about you, but this number, right, 0.99999999998, well, that's awfully close to 1, right? So I'm guessing that the limit is probably just 1. I think that's a very reasonable answer here, because from both sides you get essentially the same thing. You get 0.999999998. And again, that's very close to 1. Okay, so the limit is 1. And you get that just by using this table here. Okay, yeah. Now, what happens if you try to plug in 0? If you calculate the sine of 0 divided by 0, well, the sine of 0 is just 0. And 0 divided by 0 is not 1. 0 divided by 0 is indeterminate, right? It's undefined. It could be anything. Indeterminate. Yep. Right. If you remember in the previous example, 0 divided by 0 was actually equal to 3. In this case, 0 divided by 0 is also equal to 1. Right? I can say 0 divided by 0 is 294. So who's right? Right? Which is it? Is it 1? Is it 3? Is it 294? Yeah, it's all of it. It could be anything. Right? So that's the whole point of 0 divided by 0. It's meaningless because it could be any number you want. Right? And so we just don't define it. We don't give it a value. Right? That's why we call it undefined or indeterminate. But that's not the answer. Right? The answer isn't, right, what is the sine of 0 divided by 0? That has no answer. It's undefined. The question was, what's the limit as x approaches 0? And as x approaches 0, right, from both sides, left and right, the y values just get closer and closer to 1. So the limit is 1, even though the function itself is undefined. Okay, and you can see that if you look at the graph. That's not a vertical line. Let me try one more time here. That's a little better. Okay, so here's the x-axis, here's the y-axis, and I'm going to try to graph the function sine x over x, right? And yeah, so way over here, this is going to be pi, this is going to be 2 pi, this is going to be minus pi. Again, we're using radians, so units of pi should be a little more clear here, right? And then this is going to be 1/2, this is going to be 1, this is going to be 1.5, and so on, right? So the graph will look something like this. Oh, a little sloppy here. Okay. So this just kind of bounces back and forth. And I'm not done yet. Got to fix this mistake up here. Oops, sorry about that. There we go. So here's the graph, right? Sine x over x. What's happening, as x is getting close to 0, we're approaching the y-axis here. The y values are getting close to 1. But you never get there because, once again, there's a little hole in the graph. You're missing that point, right? When x is 0, y is not 1. So there's a hole at the point 0, 1, which means, again, when you plug in x equals 0, there is no y value. There is no point here. It's missing. But for the original question, as x is approaching 0, the y values do get close to 1. They just never get there. They never make it to 1. Right? These numbers, right, 0.99999, you can get as close to 1 as you want, just keep repeating the 9s, but at some point you got to stop writing the 9s. And in that case, you don't get 1, you get something approximately 1, or very close to 1, right? Now don't confuse that with 0.9999 repeating. That does equal 1, right? That does equal 1. And you might say, well, wait a minute, that's ridiculous. The 0.9999, that's a different number. It's not 1. So there's two answers to that. One, so this idea that just because this does not look like the number 1 doesn't mean that it isn't 1, right? I can write any number of different ways I want, right? The number 2, right, looks like 2. It doesn't look like 12 over 6. But they're the same number, and I know you know that, right? 12 divided by 6 is 2. So we have two different ways of representing the same number. Likewise, we have two different ways of representing the same number. You can write it as 1, or you can write it as 0.99999 repeating. Okay? But don't get confused with that and 0.99999. That's not the same as 0.99999 repeating. So once you stop repeating the 9s, once you cut it off somewhere, right, this is not equal to 1. It's only approximately equal to 1. Whereas the 0.9999 repeating is equal to 1. Okay. So I hope that helps. I'm not going to get into why 0.9999 repeating is equal to 1. You can look that up if you're interested. It's interesting, but one that would take us a little bit off track here. So we did it both ways, right? We did it numerically, we did it graphically, and we got the same limit. We got 1 as our answer. Okay, but this is another situation where you cannot find the limit by plugging in the number. In some cases you can, but not in this case, right? And you know, if you look at this carefully, you might know when you can plug in the x value to find the limit, and when you cannot. If you have a hole in the graph, you cannot plug in the number x to find the limit there. But when you don't have a hole, right, like if I wanted to do pi over 2 here, there's no hole in the graph. There's an actual y value here. So if you want to find the limit, you might as well just plug in pi over 2. But you have to know the difference. You have to know when you have a hole in the graph and when you don't. Until you know the difference, without actually graphing the function, that's sometimes very hard to tell. Okay, and so yeah, so we're going to get into that in the next few videos, in the next few sections. But I hope this at least helps finding limits numerically or graphically. So there's a whole bunch of exercises in the book. Do as many of those as you can, and that should give you enough practice, I hope. So that's it for this section, finding limits graphically and numerically. Again, read the question carefully, right? Don't do it graphically when it says numerically and vice versa. And maybe a few cases you might want to do both, but usually just one or the other. So numerically means make a table, right? This table over here. And graphically, again, draw the graph. Just try to draw it as neat as you can. You know, mine's a little sloppy here because it's just hard to do it on this little tablet, but you know, hopefully you get the idea. And yeah, so that takes care of this section. The next section will have to do with calculating limits again, but we're going to learn a very slick way to do it, because obviously numerically it's kind of sloppy, it's kind of tedious, right? It's not a very pleasant way of doing it. And again, because my graphs are a little sloppy, same thing. So we'll learn a very slick way of doing it in the next section, next video.